This is technically lecture number 25, which we are doing over here. The contents of today are the slip ring induction motor, the design classes A, B, C, D, and the torque slip curves. This is actually SO from all over here. We are going to talk about the deep bar and the double cage rotor as well. I will show you. This is actually lecture is most comprising of the construction details so that you can change the torque of it. So then, and the last end, we are going to talk about the speed control of induction machine. This is article number 6.9, but we will do some only choosy parts of that article. So this is today's article. Today's lecture is related to article number 6.6 and 6.9. But before I go on towards the slip ring induction motor and the design classes A, B, C, D or E over there, just a little brief from the last lecture, lecture number 24, for those who have still not gone through this. In yesterday's lecture, we actually developed a torque slip curve. So what was the torque slip curve? I told you in the last lecture also that the torque, whenever a motor is being discussed, we are interested in finding out the torque speed curve. And since we are talking about an induction machine, so an induction machine, we know there is an NS and NR, and this means that the rotor is actually trying to catch up with the stator magnetic field. So there is a slip in relation with these two, and that formula was NS minus NR divided by NS. And if you want to convert this into slip, then you have to percentage slip, then you have to multiply it by 100. So induction machine curves are always given as torque slip curve because the rotor is trying to slip or is trying to catch up the stator magnetic field. For that purpose, in a brief overview, this was the equivalent circuit. In this equivalent circuit, we took this RC out of the circuit. This RC was the lumped stator eddy current and hysteresis losses. So this was taken out of it for reason that this is going to be ignored because the core losses plus friction and windage, we are assuming they are constant throughout the load profile. So this was our equivalent circuit, and based on this equivalent circuit, whenever we need to find out the power that is actually being dissipated, we need to find out the power in this resistor, and this resistor is R2 by S. And the power which is being dissipated inside this one is air gap power. And the air gap power, you already know it from your last equation of the chapter. This one was 3I2 square R2 by S, and I2 is the current over there. Now the problem with the last lecture before even this lecture, lecture number 24, is this, that you have to first of all calculate I1, and then based on this you have to calculate I0 and then I2 by current division rule. Now the problem over here is that the circuit is having a lot of resistances, impedances, and this path in resistance. So you have to apply a current division rule after finding out the total impedance of your circuit. Now here comes the important thing, and you are going to apply the Thevenin equivalent circuit by how you are actually going to convert this portion of your circuit, because this is actually having the source, the stator part, the air magnetizing, air gap magnetization. So you are going to actually have these three elements converted into its Thevenin equivalent circuit, and at the end of the story, your Thevenin equivalent circuit will now be just a very simple circuit, something like this. This is a series circuit where you have a V Thevenin source, you have an R Thevenin, you have a JX Thevenin, and then everything is in series. So now when everything is in series, the path becomes easy because now you have to calculate only I2, and this I2 is just going to be equal to V Thevenin divided by the whole impedance which is in series over here. And in series, you all know this is R Thevenin, this is R2 by S, this is X Thevenin and JX2. So I hope so you can go through this proof yourself by converting. You already are familiar with the Thevenin equivalent circuit from your CAD 1 course. So you can go through this V Thevenin, equations are there. The proof is available in lecture number 24. So this is your Z Thevenin being found out. This proof is not a part of your book. I have made this available. I will share the screenshots on MS Teams also for this one. Kindly go through this one. Sometimes in the exam this is asked that you have to find out R Thevenin and X Thevenin. So if the approximate values are for R Thevenin and X Thevenin is this, or if you are interested in the exact values, then you can use R Thevenin and X Thevenin. And I told yesterday also that if you have a question of like just 3 or 4 marks and you are asked to only find out supposedly the torque over there, so for the torque you only require PAG divided by omega S. For PAG you need to only find out I2 over here. So the first thing first, you know X Thevenin is equal to X1, you know R Thevenin is equal to this form, and V Thevenin. So just use of these three equations, you can easily come at your I2. And based on this I2, when you have got your I2 over there according to this relation. So when you have got your I2, you can use this I2 in your equation of 3I2 square R2 by S. So when you have put in this equation, you get your final air gap power in this form, and you have to divide this one by omega S to find out your torque over here. And this torque was the final outcome of lecture number 24. So here this torque equation is the main general torque equation over here for an induction machine, and this is called as the torque slip equation. Now in this whole equation, the variable quantity is S. So here R2 is also constant, R Thevenin is constant, X Thevenin, X2, R2 by S, omega S is even constant. So S is the variable quantity. So when you want to plot this equation, you are actually going to move this slip from supposedly 1 up till 0. Now at 0, the torque is actually going to be infinity by according to over here. So here in this term, slip is going to be changed from 0 to something like 0.0001. And when you are going to plot this one, you are going to get a torque slip curve something like this over here. And in yesterday's lecture, I talked about that this torque slip curve has three very important quantities. One is called as the T start, the other one is called as the pull out, and the other one is called as the full load torque. So the only point of concern or interest is only this region over here, where actually the full load torque from approximately the no load torque is actually being produced over there. So this is the actual torque slip curve. The point of interest is only this region, but we are also interested in this torque start. Why? Because when a machine is going to start, it's going to produce this amount of torque, and when this torque is being applied, you are going to actually come up with this point, supposedly at full load point, and it's going to come at this point. The pull out point is important because this is the maximum torque the machine can develop, certain to some conditions. Why? Because if the machine is designed from this value to this value, it is going to perform well, but if your winding can handle a current, then you can take it up till this point, and then after this point the torque starts to reduce down for some obvious reasons which I will tell you in the later classes. But over here, this pull out point, the torque start, and the full load point, these are of our common interest over here. So this torque slip curve actually is always plotted. Now this torque slip curve, one thing before I move on towards today's lecture, if this curve is in front of you and this is the torque equation which you have plotted based on this one, what will happen if you change R2? Obviously, you can see if you are going to change R2 over there by seeing this mathematical equation, your first answer would be that torque will change. Yes, torque will change, but if you plot for a different value of R2, the same curve. Understand this question? If I plot R2 for same all values over there, and certainly when this R2 is changing, this R2 by S will also be changing. So when you are going to plot the whole curve from supposedly the slip of 1 up till 0, the curve is going to be something, if I plot it again over here, and I told this one in the yesterday's lecture also, that your curve will be something like this over there. Now what is happening over here? Supposedly my resistance of R2 was R2 dash, this one was for R2, and R2 dash is greater than R2. You can prove this by your MATLAB, any solution over there or Simulink, you can actually perform this one and get the answer why this is happening over there. But the point over here is that if you have changed your R2 to R2 dash, you have actually achieved something. A machine which was only rated for 100% torque is now producing approximately 400% torque in starting. But the disadvantage is also there. When it starts, it has to come in this region over here, that is going to be this region, because you are going to produce from 0 torque to the full load torque. So now what is happening, the speed variation is now very large. So when you are going to go from your no load point to your full load point, the speed variation is extraordinarily large. So this technique is used in your slip ring machines. And in slip ring machines, I am talking about those machines where you are actually going to have the rotor terminals coming out of your machine. So you have also this machine, I told this one previously also, that you have this machine in the lab. Only one machine is there, which is just beside the left of your door entrance of your machines lab. And in that lab, you have, in that machine, you have 3 windings over here, which are called as UVW. These are the stator windings over here. And then you have 3 terminals over there, which are called as ABC. If you have seen that machine, you must have performed an experiment. So what you do normally, you short this A, B, and C. And when you short them, you actually make it as like a cage machine, which means a squirrel cage one. But if you don't short them and you take out these 3 wires and you connect a variable resistance over here like this in Y configuration, you can actually change the rotor resistance. So when you can change the rotor resistance, you are actually going from this R2 to some value of R2 dash. So the advantage is huge that you can actually have a starting torque large, and then when the machine comes in this region, which is our interest over here, because here you are getting a large amount of slip. So what you can do, you can change this resistance back to its original value, or you can make it 0, and now your machine will be back to this curve. So now your region of interest will be back to your original one. This type of machine is called as a slip ring machine because the 3 terminals coming out are actually using the carbon brushes and the slip rings. And this type of machine is expensive as well, almost 5 to 10 times expensive, because the winding is actually coming out and those 3 terminals have to be attached to an external resistance. But the advantage is huge because you can actually change the starting torque from one value to the other. So when you can change the starting torque, you can actually use it for elevators, lifts, or cranes or something like that, where the starting torque requirement is huge. But when you have done that, you don't want to operate it in this region because here the variation of speed is very large. So you take it back to the resistance back to this one, and this is only possible in your slip ring induction machine. Now, if I go on towards your today's lecture, I have this curve over here. Can't find that curve over here. Actually, just let me type it out. Maybe I have it here on, I don't know, I want this one. But anyway, I will draw this one over here on this curve. If I have this curve over here and so I can have a lot amount of slip ring induction motor curves based on this one. So if I have this blue color over here, I can make another curve like this, and I can have another curve supposedly maybe for maybe like green color, and this will be actually having a little bit different. So now let me just change this value. Supposedly from R2 you are changing it to let me use some different color. This is R2 dash, this is R2 double dash, this is R2 triple dash. Now what I have done over there, you are actually changing the rotor resistance in such a way that your R2 triple dash is certainly larger than this one. So this is certainly larger than this one, and your total resistance is being changed over there. This type of machine where you can actually do this thing, we can have a variable resistance, you can actually change the starting torque. Now, I don't know, I'm perfectly right on this part, but I don't know how many of you are interested in the Tesla car, the electric car, the Roadster, which they have introduced. They have not yet given the patent design of it, but they have achieved a time of approximately 0 to 1.8 second. They are doing it, that 1.8 second for 0 to 100 kilometers per hour, which means they can go from 0 to 100 in just 1.8 second. And this is the highest speed acceleration for any car in this world, even more than Bugatti or Lamborghini or any other car over there in the world. So practically they have an induction machine over there in their car, and they have three motors actually. 2 are in the rear, 1 is actually in the front of their tires. So practically what I think, how they are actually achieving it, because they need a rightful acceleration at the start. So maybe their rotor is not based on this resistance over there, because when you are going to have a resistance using your carbon brushes are going to have a lot amount of efficiency issues. So practically this is not the solution which they are doing. But yes, you can have a solution in such a way, maybe you can develop that solution, that your rotor is still fixed and your rotor is rotating, and you wirelessly give a signal by some communication channel to your rotor, and inside that rotor you have a power electronics unit which can change the dynamic resistance of that rotor. Okay? This is just my proposition based on some study I have done it. So this is my proposition that this may be the solution that they have taken out, because from an induction machine taking 1.8 seconds for 0 to 100 kilometers per hour, this is phenomenal. The previous best was approximately 2.26 seconds from Bugatti. So this was the time over there. So if they are taking this, it's still not on the road. It's still in the design channel, or I guess in the production channel, the Roadster 2.0. But the possible solution which you are getting over here, which I can actually understand, maybe they have a big motor also, maybe they have some other thing, but the startup acceleration is so huge, they can actually achieve from, I guess, 0 to a quarter mile in maybe like just something 5 seconds or 6 seconds, something like that. So the time is phenomenal, and that is only possible when you can actually have a very huge starting torque. So Tesla, you're rightfully using the induction machine over there. An induction machine, one thing very important, many of you will be going on towards some final year project related to your electric vehicles, because that is the boom of the day today nowadays. So electric cars normally use induction machines by Tesla. If you're talking about a Nissan Leaf, then Nissan Leaf is a very good electric car used in UK or Europe, or maybe somewhere in USA also, in California. So that car uses a synchronous motor, okay, which we'll be talking about, PMSM, permanent magnet synchronous motor. And if I talk about a BMW i3 or BMW i8, which is a hybrid car, it uses a BLDC. The normal hybrid car in our Pakistan, the Prius, Toyota Prius, it uses a BLDC also. So normally the talk of the town is BLDC. But BLDCs use permanent magnets, and those permanent magnets have a cost of 50% of the cost of the magnet is taken up by that cost of the whole machine. So if a machine is supposedly $100, that cost of that $100, $50 is for the permanent magnets. And sadly, permanent magnets, China has the control on permanent magnets, almost 70 to 80% of the magnets. So normally, whole of the world, the western side, the Europe and USA, they don't have that much leverage to go on towards the permanent magnet side, because permanent magnets are not just now coming on naturally. They have to be made artificially using ceramic material, and almost 70 to 80% control on the permanent magnets is by China. So at present, world is looking on towards the Tesla car, the induction motor. Yes, it has a little efficiency. If you are talking about an induction machine, the efficiency can only reach, the maximum, I guess, is going from 85 to 90%, not more than this. In fact, in normal range, I guess I will only call it 80 to 85%. But if I am talking about a BLDC machine, I am talking about an efficiency range of approximately 90 to 95 also in some cases. But yes, BLDC, it has some problems. There is a degradation taking place. I don't know how many of you have driven a Prius car. The Prius car is a hybrid car which can have a 0 to 60. It works on the electric vehicle. But when you change on from, or you go on from the 60 to approximately 100 or something like that, the gasoline engine turns on. So, but normally the people in Pakistan, they don't know this thing, and they are actually driving it at like 70 or 80, and then you are not consuming the electric part of that vehicle. So normally the Prius is the best car as such. And actually I have worked on its battery management system. It has a 210 volt battery pack inside it, and I've actually opened it and tried to reverse engineer that part. So actually I have an idea on that part. So this is a little talk on the electric vehicles, because this is the talk of the town at present, and since induction motor is being discussed, so my guess is this, that the slip ring induction machine, little converted wirelessly, because you can't use those slip rings, is actually the design of the Tesla Roadster, by which you are achieving that phenomenal acceleration. Now coming on to back to our in Pakistan, just to give you an idea on the induction machines, in our lab, UET has a very different type of machines. They are approximately 20 years or 25 years old. But I developed a machines lab in LUMS quite few years back, approximately 8 years back. And I imported some machines from Europe, Daladenzo, and from Japan, Turco over there. The size of the machine was phenomenal. For example, the size of the machine was not more than the thickness of this projector. I'm talking about the width over there. And the horsepower rating was approximately 2 horsepower or 3 horsepower. And just to give you an idea, I don't know how many of you have seen some YouTube videos on Tesla or something. Some years back, I went to Dubai, and there was some tear down of a Tesla car. There was some engineer there, or maybe hobbyist over there. He had teared down his Tesla. जो कि खैर वारंटी वाइड हो जाती है and all that stuff happens. So उनकी जो मोटर है that is approximately 340 horsepower and the size is just double of this projector. So you can understand that material that is being used inside that motor, the technology being used inside that motor, and the size of the inverter which is used to run that in Tesla or the induction motor over there. So we are actually lagging behind a lot. So वो machine जो मैंने आपके लिए makers lab में रखवाई है, that machine has a horsepower of approximately just 1.5 horsepower, and you can see the size, the weight of that machine. Pakistan के अंदर the problem, as I told you previously when we were discussing transformers, the problem is this, that we don't use the best quality silicon sheets. The silicon sheets have gone, the material, the metallurgy material have gone a lot up, but in Pakistan we don't have access to such materials and we want to earn a big profit in small time. So normally we are using the baddest silicon sheet, not even silicon sheet, we are just using simple sheet. Or आपके पास when you are clamping up sheets together, one thing very important, I told you previously also this one, when you are stacking up sheets together, you have to put some resin in between. By resin I mean there has to be an insulator in between. लेकिन पाकिस्तान में if you have gone through it, वो ट्रांसफार्मर हाल रोड पे अगर आप कभी जाओ और आप उनकी शॉप्स में पीछे बैक साइड पे आप देख सको, what they do it, they stack up all the laminations together, वाइंडिंग कर दी उसके ऊपर और उस पूरे ट्रांसफार्मर को वाइंडिंग करने से पहले सिलिकॉन के अंदर डिप करके कह दिया हाँ जी सिलिकॉन लग गई है. So this is not the way. This is not the way. You have to put by brushes on each sheet the silicon, and this process is done by the final year students of DEM who are actually studying this course of design of electric machines, the next course after this course of yours. So they have done it by brushing. It's a very untidy work because it's very sticky also, and you have to put it by brushes. But the final year students, they have done this work. So in Pakistan, normally very small companies or very little quantity of companies, they are actually working. One of them is KSB Pumps. I don't know how many of you have heard this one. They have a plant at, I guess, at Haripur or somewhere else. I guess the location is there. They are doing a wonderful job, but they are also the official distributors of some Tesla motors in Pakistan. Tesla is not just producing the cars motor, they are actually producing some induction motors also for the private world also. So they have also that business as well. Okay, ji, coming on to this one. Now coming back to Pakistan, we have only 4 design classes in Pakistan, design class A, B, C and D. So we have to come back to our original and how this A class, B class, C class and D class are defined. So one thing very important, whenever these design classes are being discussed, what we want a very high starting torque. We want that this region is very small. So we have to make a motor. We know the solution is slip ring induction motor, but that's expensive by using slip rings and having a variable resistance and all that stuff. So the solution is this, that you can have a motor which has a high starting torque and then afterwards it goes on and follows this trajectory over there. So we want something like this, which can have a high starting torque also, and then it comes on and makes something like this. Because we want a high starting torque also, and we can't change the resistance externally because that makes the cost of the machine a lot large. You have a maintenance problem also. So what we are actually interested in, this is our curve over here, and in this curve you can see I have shown 2 curves over there. One curve is the low R2, which means that if you have a low R2, you have this curve over there. The second curve over here is a high R2, which you can see because it has a high starting torque. But now the region of working, supposedly if this one, let me mark this one over here, maybe with the red color. So if I have this, supposedly this is the torque full load point, and supposedly I am interested in, so this machine is going to have the variation from this point to this point, and corresponding to this, the speed variation is just this. But when I'm talking about the other machine, supposedly this one is going to have a variation in this region over there. So this variation or this slip region, this percentage slip is very large as compared to the other machine. Now what they have done over there, you are going to make a machine somehow by taking the construction into consideration, which is going to still have a reasonably high starting torque, this dotted curve, and try to have also a very small slip region. How this is going to be done, this is very important, which means that I am actually going to design a machine which in this case, supposedly if I mark this one, this is my slip over here, and here the slip is 1 and here the slip is equal to 0. So now I want to actually design a machine which will be having at slip of 1 a high resistance, but when it goes towards the low slip, that is actually the normal operating region, it will be having a low resistance, which means that a rotor is going to be designed in such a way that it will have a dynamic resistance by construction. Now how this is going to be done, you will just see today. So this is the actual output which we require by combining this curve and combining this curve over there, so that this dotted is actually our acquired result, which is the important thing. Why we want it? Because we need a high starting torque, we need a low region of the load manipulation from the zero load to the higher load form. Now based on this one, this are the 4 classes over there. Class A is the most simplest of that form. If you can see, don't go towards class C and D at present. I am only interested at present in class A. Now class A at present is the normal induction machine, which is made in such a way that it has a reasonably starting torque, and this is based on pull-out torque over there, and the region of interest is not more than if you slip over here, maybe like 2% or 3%, not more than that. But if you see class D is the same, having a high R2. So what we want to do now, I want to combine class A and class D and make something class B and class C. The class B and class C, they have a slight difference. If you see, class C has a higher starting torque, class B has a little small, but overall their curves are almost similar in the low slip region over there. How we are going to do it? Very simply, class A and class D, they are very simple, because class A is going to be made with a low R2, which means and class D is going to be made with a high R2. Now first of all, before going on to class B and class C, I have class A and class D. How to make class A? Now these are 4 rotor stampings. These are the rotor cuttings over here. Since I told you that eddy currents are also going to be there inside the rotor. They are going to be small, which we are ignoring them in our calculations, but they will be still there. And since the motor is going to start from 1 slip and then going on towards something 0.01 or 0.02, this means that you have to have eddy currents. Those eddy currents have to be stopped, so you have to use laminations. So these all are actually laminations over here in your rotor. Now, which one corresponds to which? Let's see that. The first diagram which you are seeing over there, these are the rotor bars which are over there. Now, when you are going to stack up all these together, you are going to put your molten aluminium or molten copper inside these ones and stack up all this together and make a rotor. Now, if you see and compare, supposingly, this diagram with this diagram, can anyone tell me the difference in these two, A and D? I'm talking about A at here. This is my A diagram. For those who can't actually see this one, this is, I have this one as A, this one as D. Can anyone tell me what is the difference over there? Certainly this is design class A. This is design class D. G. Can you tell me the difference by seeing these stampings? I am talking about these stampings, this one. So this is the covered area inside it. And certainly when I am talking about this one, G. Can you compare this? क्या है? Bars छोटी हैं. क्या होगा उससे? They are in larger number, but bars are small, which means that they are going to have a little higher. If I call R bar, the resistance of 1 bar supposingly, if you compare the R bar resistance of this one and this one, certainly you are going to have G. किसकी ज़्यादा होगी? D की ज़्यादा होगी, of course, because here they are only accustomed to the initial one over there, so they are only in the very small region. So R bar of this one certainly is larger than this one, and we all know if R bar is large, if I go back over there, you are going to have a high starting torque. And for class A, starting torque is still there, but the advantage is in the region of the low slip one. Now, not just R bar, Will there be any effect on x2 of this? X2 of this. First of all, tell me what is x2? जी रोटर की नहीं, क्या कौन सी रिएक्टेंस? लीकेज रिएक्टेंस, रोटर्स लीकेज रिएक्टेंस. जिस तरह से आपके पास स्टेटर की लीकेज एक रिएक्टेंस थी, you had a stator leakage reactance, and I told you that it will be a little larger than its counterpart transformer part because it stays inside the iron core, and the one which goes towards the rotor, that is actually of our interest. So the one which remains inside the stator core, that is actually JX1 or symbolizing JX1 over there. Now when I'm talking about the rotor, now see this very carefully. When I'm talking about the rotor, I'm talking about this over here. Let me just take this off. Now over here, if I am talking about this conductor over there, certainly supposing it is not just molten aluminium or copper placed over there, assume that I have, let me use us. I have conductors over here, this one, this one, this one, and these are all conductors placed over there. Now tell me, if flux is being produced by this conductor, supposedly this is a cross, 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 and all of these at that one time over there. These conductors, let me change to a different color, maybe black, not black actually, yellow is good. Now this over here is going to produce a flux over here, and that flux will be linking with the stator. So this is my stator, and the flux, in fact yellow is also not good, which color I should use? Black. So if I have this flux being produced, the flux will be coming in the air gap. This is my air gap. So the flux being produced by the rotor bars, it has to reach the air gap or the stator part so that it can have the effect of the current on force on a current carrying conductor placed in a magnetic field. Hona kya hai? If I reiterate your previous classes, what we did, this conductor was going to produce a flux. This flux was going to react with the air gap flux over there, that was B over there. In other words, this is called as BAV actually, B average over there. When this reacts with this one, it is going to develop a force F, and the force F is going to be exerted. But the conductor which is over here in this region over here, which is very deep, this flux is not going to reach over there. It's not going to reach. So what is going to happen over there? X2 of this type of deep rotor bar is going to have a large X2. I'm again repeating all this. Please listen this carefully. The flux which is being produced by this, like maybe 3 layers of the conductor, supposedly they all have a cross over there, they will be producing a flux which is shown over here by this black and yellow lines over there. They are reaching the air gap, they are interacting with the air gap flux, and they are going to produce that force F, that is actually the induction motor torque being produced over there because of that force. But the conductors which are very deep inside the rotor, their flux is not going to reach the air gap. Their flux will remain inside the rotor and they will increase X2. So what is happening over here, in your design class A, your X2 is a little larger as compared to your design class D. Your X2 is here very small. Why? Because the bars are not deep. They are not inside the rotor. They are very small in number, but they are closer to your stator. So even if your stator is being produced over there, this is your stator, and you have a conductor placed over here, here. Their flux is going to be linking the rotor and the stator over there. This is the air gap over there. So you are going to have the flux over there. Now, can anyone tell me here in this case, X2 is going to be on the smaller side. What advantage will we get if I am having a difference in X2? R2 का difference हमने देख लिया, because here the R bar resistance was smaller. Here R bar resistance was on the higher side. You were getting a high starting torque. What advantage will X2 give? Because here in this case X2, here in this form, your X2 over here is certainly, let me call it, supposingly, let me call it x2a, here is going to be certainly larger than the x2 of design class T. What is advantage? What advantage or disadvantage I am going to get in the two design classes? G, anyone? Any idea on this one? किसमें? x2 small है, losses कम होंगे. जी, any other idea? And why? Why losses कम क्यों होंगे? Okay, current is going to be smaller, but current कम होगा तो आपके पास torque भी कम produce होगा. Remember that thing also. अच्छा, whenever you are analyzing a torque slip curve, always analyze it with respect to two regions. The two regions are starting torque and the full load to no load region. Now, let's analyze it with respect to starting torque. Now, at starting, remember this thing, at starting, your slip, let me change it to color, you are at starting, when the machine is starting from rest, your slip is equal to 1. Light? Yes, light is gone. Achha, anyway, let light will come. When you are going to have at starting, your slip is equal to 1. So when slip is equal to 1, x2 is equal to 2 pi f L2. Now, just on it. Okay, ji. Now, coming back to what we were discussing, we were talking about the x2. x2 is the leakage reactance of your rotor. And I'm talking about with respect to design class A and design class T. And we decided and we came at this solution that x2 for design class A is larger than the x2 of design class T. So what advantage or disadvantage will it get? Now, we know when the machine is starting, it is going to have a slip of approximately 1 or closer to 1. And when the machine is near the normal range or the normal load to full load, then it is going to have a slip in range of something 0.02 or 0.04. Now, when this slip is changing, if you remember, we converted our actual performing equivalent circuit into a mathematically easy to solve circuit. So we changed your x2 and we changed your rotor voltage also. Now, at this present time, since we are analyzing the motor from its practical point of view, so we are going back to this original circuit that was happening. Now, when the machine was starting from rest, that is slip 1, this was maximum. The voltage induced inside the rotor was maximum because of the relative velocity factor over there. This RR was the resistance. That was constant. It was not changing. But yes, this JS 2 pi Fs was your rotor resistance over there, and corresponding to this one, because your rotor frequency was dependent upon S, so your Fr was equal to S times Fs. So when your slip is equal to 1, your rotor frequency is also 50 Hertz if you are working the machine in Pakistan. So this means your X2 is going to be larger. Now practically, here the leakage reactance is large as compared to this one. And normally when the machine is going to start from rest, it's still going to be on the higher side. So this slip is going to be a very critical factor when the machine is starting. Up class D के अंदर you already have a low X2. ठीक है, आपकी leakage reactance बहुत कम हो रही है. Here in this case, the flux is not remaining inside the rotor core. It is linking with the stator more. So, but here in this case, slip अगर 1 भी हो जाएगी, it's not going to have that much effect over there. But if you compare this one with your design class A, here your leakage reactance is a larger quantity. So here when your slip is going to be 1, your X2 will be a little more higher. So practically for design class A, if R2 is higher or small, is smaller, your X2 is higher. So these both quantities are going to try to cancel their effect over there at starting. But since we have made this one over here in deep bars, so your R2 is very, very small as compared to the X2 effect which you are getting over there. So normally in design class A, you can see you have a substantial starting torque. And when you go on towards the low slip region, your speed variation is very, very small. But if you compare this one with your design class D, Here your x2 is very, very small. So even at slip is equal to 1, your effect is not going to be that much prominent. And that's why you can see that you have a very, very increase in your starting torque over there. x2 पहले ही कम है, slip 1 भी हो जाए, still it's very small. So you are getting a very substantial increase. Why? Because your R2 resistance is controlling the starting torque over there. And coming on to back to your section over there, in this equivalent circuit, in your equivalent circuit, if this R2 by S is smaller, X2 is also smaller, your I2 current is actually increasing. And when this is increasing, I2 square R2 by S multiplied by 3, this term is, actually, let me go on back to that one. This term over here is the important thing over there, because this air gap power is being converted into its torque over there. Now these are two design classes, class A and class D. Now compare your class A with this design class B. So if I have now, this is design class B. Now since you already have seen this design class B curve, the class B curve is almost the same. It's not that much difference as compared to class A and class B. But physically, if you see these two, can you tell me the difference? A slight difference over there, not much difference over there. The bars are a little deep. The bars, here they are not having that much distance with the enter. Here they are going a little more deep, and your X2 in this case is going to be a little larger. Okay? Even at starting slip or even at low slip, whatever happens, your X2, or let me call it in the terms, don't use the word X2, because X2 is made up always of 2 pi FL2. So let me use the word L2. So leakage inductance is going to be larger in this term. So here in this one, design class B, you can see what is happening. The pull out torque point, there is a visible difference over there. And why this is happening? Because X2 is larger. So when X2 is larger over there, you have a little. But normally the starting torque, they both are almost same. The region of interest, which is actually the no load to full load point, they are also good. But now the important thing is what has happened in class C. In class C, you have achieved a high starting torque and you have achieved a low slip region also. How this is done? Let's go on to this one. Here in design class C, you have made a 2-slot mechanism. What does this mean? This means that you have actually made one slot here, taking another slot into 2 slots. This type of slot is called as a double slot mechanism. Now what is happening inside this one? Here, this conductor which is going to be placed in this upper slot and the conductor which is going to be placed in this lower slot, they both are going to behave differently. This is very important. Here, let me call this one, let me use over here, let me call this one as supposingly slot upper, let me call it slot U over here, and let me call this one as slot lower. So this is slot lower, this is slot your upper, closer to your stator. Now, question over there. Dono slots ko if we analyze separately. Now, question over here is it, will this slot upper is going to have X2, or let me call it, don't use the word over here, let me call it L2U. Will it be larger or will L2 this lower? Which one will be larger? L2 lower, because this is closer in the rotor. So L2 lower will be higher. So this means that X2 of this one as compared to X2 of this one, there is going to be a considerable difference. Now, here the tricky part comes in. The tricky part is here. Let me go on to this one. Treat this slot shape which is shown over here as the same 2-1. In the book, they have actually done this mistake. This one, treat it as the same slot. Let me use a different color. So this is, treat this one as one slot. And then afterwards, you have a connection and treat this one as the other slot. So what you have done over there, this region, let me mark it. This region is that upper slot. And this region is that lower slot over here. Now, Same thing over here. If you copy this one over here in this slot, so you have over here, let me use the same colors over there so it's easy. And you have this one, the lower slot, and here you have that upper slot. And if I go back and make this slot over there, this is your slot. So I have now, in this case, this is the upper slot, this is my lower slot, this is my upper, and this is my lower slot. Now, what we need, we require a high starting torque, and for that, what I require R2 to be higher. But when it goes on towards the low slip region, I want the resistance to be decreased. Now, how this is going to happen? Since this upper and lower, they both are connected together, and since all these bars are coming in parallel, okay, I hope you understand this thing. This over here, the pink color, the yellow color, they both are connected together, and I told you they are not made up of some wiring, they are made up of some molten aluminium or copper which is placed inside these two over here. So they both are in parallel. They are not in series, they are in parallel, which means that this bar, this bar, this bar, this bar, all of them, they will be in parallel. So if I am talking about one bar, their resistance is going to be in parallel as shown over here in this 4. Now, the interesting part, if I am talking about the upper conductor, it's placed over here as a cross. It's going to link with the stator better. Its X2 is going to be smaller. And you can see the L has been shown smaller. And here smaller is shown because only 2 rings are shown, or 2 times you have made that solenoid here. But if your conductor is placed in the lower, it's going to have a larger inductance or leakage inductance, and it is shown over here as L3. So I hope this diagram is clear. Here, these two you can take them from the upper, these two are from the lower. It's just a physical representation, how to represent it, because you have put molten aluminium here or copper here, molten aluminium or copper here. So now this R and R and R, they all are same. Now the point is still not achieved that aapne R bhi same rakha hai. If supposingly this resistance was 10 ohms, for example, I'm just taking a 10 ohm, it may be something in milliohms or microohms, it will be smaller. So all of these are supposedly 10 ohms, 10 ohms, 10 ohms. The overall resistance of one bar will be approximately 2.5 ohm. But here the tricky part comes in. Because the inductance is different, inductance for each path is different, and when the machine is going to start from rest, your slip will be equal to 1. So what will happen? The X2 or X3 of this one will be larger than your X2, will be larger than X1, will be larger than this simple X. I'm again repeating, listen this carefully. 4 parallel paths, each is having a different inductance because the leakage reactance over here, or the leakage inductance, let me use the word leakage inductance more. So this one is having a larger leakage because this is closer to the rotor and farther from your stator. So here L3 and L2, they are corresponding to your lower slot. So you are having more leakage inductance. So here L and L1, they are having closer to your stator, so they are having less leakage inductance. But when your machine is going to start from slip 1, since slip is controlling X2, what is X2? X2 is the leakage reactance. That is equal to 2 pi F into L, L1, L2, L3. So what will happen? You are going to calculate X. So this X, actually this should be called at L0, X0. So X0 will be equal to 2 pi F L0, and supposedly this is as FR. This will be X1 equal to 2 pi FR L1. This will be X2 equal to 2 pi FR L2. X3 would be equal to 2 pi FR L3. And you can easily say from this one, because L3 is greater than L2, L2 is greater than L1, L1 is still greater than L0. So you can easily say your X3 is greater than X2, this is greater than X1, and is greater than X0. Now when this is the case, your impedance of the lower branch is larger compared to the other branch. compared to the other branch, compared to the other branch. So when you are going to calculate the resistance of or impedance, let's call it Z0, let's call it Z1, Z2, Z3. हमें क्या चाहिए? We want it that Z0 and Z1, they should have a smaller resistance or impedance actually. So more current flows inside these two branches, and here less current flows inside these two branches. And this can happen at starting, because when the machine is starting from rest, slip is equal to 1. So when machine is having a slip equal to 1, the impedances of Z0, Z1 and Z2 and Z3, they change because slip is equal to 1. So when you are going to put FR, because FR is equal to S times Fs. So Z3, Z2 or even Z1, they are going to be on the higher side. So more current is going to flow from this resistance and this inductance over there. So what will happen? The rotor is experiencing a larger resistance inside it at starting. And larger resistance mean that you are going to have high starting torque developed. I'm again repeating the result over there. Since Z0, Z1, Z2, Z3, they all are different at starting. Why? Because slip is equal to 1. So when slip is equal to 1, your Z3 is very high, larger than Z2, Z2 is larger than Z1, Z1 is larger than Z2. So when you have four unequal impedances, current will try to move in the least impedance path. So the overall parallel, since all of them are in parallel, their combined impedance is going to be smaller or larger over there, because all of them are having a different one. So the advantage would be that you are going to get a larger R2 resistance over there. Your impedance is larger in the start. Now coming to this region where the machine is going to work in low slip. Now when you are coming in the low slip region, let's talk on this one. When you are in the low slip region, now here the slip becomes something 0.04 or something 0.02 or 0.08. Now the difference in these X0, X1, X2 and X3 is going to be very small. पहले क्या था? S was 1. So you are getting a frequency of 50 Hertz. Now the difference is just 0.04. Very, very small difference. Because the multiplying factor is not just 0.04. Now this time, the difference in this X0, Z0, Z1, Z2 and Z3 is going to be very small. These all four are going to behave as a almost same impedance. So when they are going to behave as a same impedance, their Z equivalent or whatever you can call it, ZR, it will be very small, and correspondingly your resistance would be very small. So here this time when you are going to plot the torque slip curve of this one, you are going to get something. Now you can achieve over here class D. It's still better, but not just as class A or class B. But you are getting a very good. It could have been something like this starting from here, and it would have been something like this. But by using a deep rotor bar or a double cage rotor bar, you have achieved a good thing that you have a high starting torque also. And now you are following this trajectory where you are getting a lot of impedance, a lot of resistance being lowered here. So now you are having a variable resistance of your rotor. And this is done just by construction. And these four are just the design classes: class A, class B, class C and class D. Nowadays, I guess class E, F, G, H, there are many classes now, since this book is a little old, and when you will go in the industry, you will be seeing many lot of motors, and on each class of motor or on the nameplate, the class is written. And these classes are determined by the IEC ratings over there, that how much resistance or how much impedance or how much torque each machine can deliver. For example, I'm not asking you to memorize this one, because sometimes in the interview or questions you are asked that design class A versus design class B versus design class C. I'm not going to ask this in the exam, but sometimes in your interview question they ask it. So you should be actually memorizing it for that time also, that your design class A, for example, they have written inside over there that for design class A, the pull-out torque is 200 to 300% of it. Now if you go back to this diagram, you can see this is in the range over here. So 200 to 300%, you can easily see that your pull-out torque is something in that region. So similar data is here on page number 349 of your book. Please kindly go through this reading, not just memorize it for the exam point of view, because this is just details which are coming from the IC ratings over there. And sometimes in the interview, they normally ask you, they give you a problem. They tell you, okay, you have a machine which has to run for like 18 hours a day. You have to tell us which design class I have to use, and if that machine is not going to shut down, which means it's not going to start. So starting torque is irrelevant. I am more interested in the running torque. So based on that, you have to decide you want class A, B, C or D. Now D is out of question because D is having a starting torque large. We don't want that. एक ऐसी machine जिसको आपको बार बार start करना है. For example, you are in the steel industry, you have to bend some rod. आपने सरिया बनाना है. So when in that industry, you have to stop the machine, take a new bar, bend it. So every time you have to start that motor from rest. In that case, class D is better. And then some of these are dependent upon class D, C, B, A. They are also having a temperature scale, that how you can run those machines for 10 hours, 12 hours or 13 hours or something like that. So based on their temperature classes, you have to decide that which class you want to. So please kindly go through this page number 349 and 350. It's very important from your interview point of view. So this is 4 design classes which I have just discussed over there. So 4 design classes over here, and you have achieved this not by slip ring induction motor, you have achieved this by the variation in the rotor construction over there. Achha, the last thing which is for today is the speed control. Now this is very, very important because in speed control, you have a lot of changes that you can do. Now what you are doing in DC machine, for those who have done the experiment, almost all of you have done the DC machine experiment of speed control. There were only 2 methods of speed control which were very good. One was the field current control, because by field current control you were getting an inverse relationship with the speed. And the second one was that applied voltage or the armature voltage was proportional to your speed. Now this is a very good control because in DC machines you can only have to change field current and over here. Now in induction machine, the problem is this, that your induction machine, if you change the applied voltage, listen to this very carefully, if you change the applied voltage, your induction machine has this equation. In this equation, you are not changing R2, you are not changing R Thevenin, X2, but you are changing V Thevenin, because V Thevenin is dependent upon V phase. So what is happening? Your torque will change, but at the expense of one thing. Why? Because if I go back to your equivalent circuit, the original circuit which we started from, here over there, when you are going to change this V phase, your current is also going to change, certainly. When current is changing, this current is dependent upon this current because there is a current division rule taking place over there. And since you have changed V phase, your RC and JXM, they will be smaller. And since JXM current will be smaller, what will happen? Your flux being produced in the air gap is going to be smaller. So your torque production is going to be on the smaller side. So you are going to have less flux inside the machine if you change your applied voltage. And I guess you have seen this one at your homes also, even here, that when you are going to change those dimmers, आप dimmer से क्या कर रहे होते हो? आपने अक्सर देखा होगा dimmers are not linear. आप कोशिश करते हो जी हाँ जी वो speed हम कम करना चाह रहे हैं. But a point comes when you can even count the blades of your fan because it's flowing very slow. And because it's not linear. Because here, the V Thevenin over here is changing with the square form over there. So the total torque equation is having a square effect over there. So if the applied voltage changes, the torque effect is severe. We want a linear control. We want a linear control and with no reduction in the torque. This is very important. I'm again repeating this. Whenever we want a speed control, we want to have a linear control. Firstly. Secondly, we don't want the torque to be reduced. हम चाह रहे हैं कि speed हमारी 0 से लेके 1500 RPM तक vary हो. Well and good, no issue. But हमारी machine, if it is designed for 4 Newton meter torque, वो 400 RPM पे भी 4 Newton meter दे. at 600 rpm भी 4 Newton meter दे, and at 1500 rpm it also gives us 4 Newton meter. So torque is very important. But sadly, if you are changing the applied voltage, the torque is going to change, because if you put in the pull-out torque. Now what is pull-out torque? We did it yesterday, that your pull-out torque was dependent upon this formula. This formula of pull-out also has V Thevenin. So if you change V Thevenin, your pull-out is changing. And what is pull-out? Pull-out is still the maximum torque which the machine can develop. So now the point is hit, that how you are actually going to change the speed. Now the first thing, very important, that you did when we were discussing the induction machine as a journal, the first thing you did was that NS was equal to 120 F by P. Whenever you have a machine in front of you, you can't change the poles. Changing the poles is irrelevant. You will have to open it, do the winding again or something like that, or maybe replace the machine. It's a costly thing. Unless and until, in your book, kindly go have a read on this one, not from the exam point of view, just for the understanding. There are some machines now obsolete, but there were some machines in which the windings were installed inside those machines. If you connected those windings, the number of poles would be 4. But if you connected in some other configuration, the number of poles were 2. And I guess you have one machine in your lab, जहाँ पे आपके पास you have 3 windings in the front, you get a speed of 1500. But if you connect the 3 windings on the back, you get 3000 RPM NS. And that is because the number of poles changed from 2 to 4. This is actually on your page number. Kindly go through this one, just not from the exam point of view, just for the understanding. This is page number 365. Now such type of machines are obsolete. Why? Because you have to install both of the windings. आपको दोनों बनानी पड़ेंगी. When you are installing both of them, your cost is increasing. Plus the size is increasing. The leakage flux is going to be more. So these type of machines are now obsolete. They are not used. But this process of having 2 poles or 2 different set of poles, having 2 and 4. So every time whenever you had it, number of poles को आप 2 रख सकते हैं या 4. या फिर आप ऐसा कर सकते हैं, I call it 4 or 6. So these are possible over there. Now, the point which I am discussing here, which is the actual speed control, that is the frequency. We know in Pakistan we have a frequency of 50 Hertz. But we can have a circuit in which I am going to take the AC supply from WAPDA and I am going to convert it from AC to DC by a rectifier. And from that rectifier, I am going to again convert it into AC, but giving from a microcontroller a frequency signal of approximately 25 Hertz, supposedly. But if I'm a microcontroller, certainly this means that I can have a very different type of, by just one button or maybe by one potentiometer, I can change this frequency over here. I'm not going into the details of this one because we're just third semester students at present and you don't have any idea about the power electronics or MOSFETs or transistors at present. But the actual schematic diagram is this. You take this 3-phase AC. This is actually 3-phase AC going inside it. You convert it into your DC and that DC is again converted into AC. And that AC is going to be of different frequency. It may be 20, 25, 30, 60. Now the question here comes, when you are changing the frequency, yes, your NS will change. And when NS change, NR will change. But will it have effect on the torque of your machine? Gee, anyone? Answer this. So I'll no issue. Question is that if you are having a frequency change from 50 Hertz, I am having now this device, and this device I am going to call it, supposedly, let me give a name to it, this one. This is called as VFD. This is called as a variable frequency drive. This variable frequency drive is now giving you 25 Hertz. Now you are giving, instead of 50 Hertz, a voltage of a frequency of 25 Hertz. What will be the difference? Machine pay, of course, NS will change and corresponding to this NR will change. But will there be any effect on the torque? Will there be any effect on any other parameters inside your induction machine? And I am talking about the equivalent circuit also. This equivalent circuit which we have done in the last few lectures. जी? कैसे? हमने वोल्टेज चेंज की है, पहला क्वेश्चन बहुत इंपॉर्टेंट. हमने वोल्टेज को कोई चेंज नहीं किया, बट यस I have done a frequency change to approximately, let's call it 25 hertz. So when I'm applying 25 hertz, listen this very carefully, this is very important. You have a 25 hertz input, so this means that the value of JXM is dependent upon 2 pi FSLM. Agreed? Fs previously was 50 hertz. Now this is 25 hertz. The value of XM reduces. More current is going to flow over here. More current means that I naught current is more. So flux would be more inside the machine air gap. More flux in the air gap means that I1 current is going to be more. And I1 current more means that the windings which have been designed for a one particular value of limit current, now they are taking a more value of current. So the windings can damage itself. आपने voltage नहीं change किए, remember. So what has happened now, this XM is changed. Of course JX2 will also change because FR is equal to S times FS over there, if I am talking about the main equivalent circuit, not this one over here. So what is happening, but our interest is this JXM. When this XM is changed, it is smaller now, your current is more, this current is more, your R1 will produce more losses and it will heat up, the winding will be damaged. Machine नहीं चलेगी after some time. So what is the solution? हमने frequency कम कर ली, हमारे पास speed आ गई अपनी मर्जी की. What I was talking about, I was saying that if I have changed my speed to 25 hertz, so now NS will be equal to 120 into 25 divided by, supposedly it's a 4-pole machine. So this is going to be, how much speed? 750. So this is going to be 750 होगी ना? हाँ यही. So it will be 750 RPM. So it will be 750. So NR would be approximately something like 700 RPM if it is at something like 2 or 3% or 4% slip. बहुत अच्छी चीज़ है. By having a frequency change, I can now have a different speed. But the disadvantage is this, that the machine cannot run. Now there is only one way to do it, and that way is by also changing the applied voltage. By what I mean by this? I mean by this that your voltage and frequency. Now this is the most important thing of this course which I am going to tell you today. In electromechanical devices, that are the AC machines I am talking about, whenever you are going to change the frequency of those devices, at the same ratio you have to change the voltage. Same ratio. If you are decreasing frequency, you have to decrease down the voltage also. And I told you previously also that if in Pakistan we have a 50 hertz, हम कहते हैं नहीं जी, okay, we don't want to use 50 hertz, we want to now go in the American block and we want to be an American state and we want to go towards 60 hertz. So if I want to go to 60 hertz, supposedly, हमारी machines designed नहीं है for that purpose. So if I am going to go from 50 hertz to 60 hertz, I will have to increase my voltage. So if 220 volt or 230 volt is the input, I will have to multiply by my 230 by 1.2 factor actually, because 60 divided by 50 is 1.2. So V by F ratio in all electromechanical devices, V by F has to remain constant. This is very, very important. And if this is not constant, what happens? Your flux in the machine increases beyond a value and your machine actually gets damaged. Now, I am doing this analysis on one basis. Let me go on towards that one. Let me use your book now in this purpose. Okay, now this is your article from where I am actually talking about this one. Please see this one, this proof. Over here you have the voltage. This is the Faraday's law of electromagnetic induction minus sign for your Lenz's law. So Vt is equal to minus n d phi by dt. If I take it into its integral form, my flux over here is equal to, come on. Okay, so I have this one. Let me use the blue color. So this form of equation, phi of t is equal to 1 over np integral v of t. Now here this v of t will be equal to something, a sine wave, because I am applying a sine wave over there. So Vm sine of omega t, And flux phi of t, if I integrate it, because Vm is a constant value, it's a peak value, so sine will be converted into cos omega t, and because of the integral sign, I will be having a negative sign. Now I am not interested in the negative sign. I am also not interested in this omega m. I am also not interested in this np. Why? Because np is constant. Vm is also constant. The only thing I am interested in this omega, and this omega is equal to 2 pi f. So what happens? Your frequency actually supposedly decreases, your omega decreases, and the omega decreases, your flux is going to increase. And if it's vice versa around, your omega, your frequency basically increases, your flux is going to decrease down. So what is happening over here? We want the flux in the machine to be constant. Why? Because torque is directly proportional to your flux. So what we want that this Vm has to be changed in the same proportion that is be changing proportion to your F. So jitne ratio se aapne F ko change kiya, which means actually omega. So you are going to change Vm by the same ratio to keep flux in the machine constant. Remember one thing, in all electromechanical devices, your V by F ratio has to remain constant. This is very much important. This is true for your transformer also. This is true for your induction machine or any other machine, synchronous generator, motor, whatever. The voltage divided by frequency factor has to remain constant. And one thing very important, यहाँ पे एक और बहुत important चीज, if you are increasing your frequency, ठीक है जी, मेरे पास एक machine डिजाइन थी that was designed for 50 hertz. मैं कहता हूँ नहीं जी, I am now going to give it a very high speed. मैं चाहता हूँ जी कि मेरे पास जो synchronous speed आए वो कुछ thousands में आए, 10,000, 14,000, something like that. I increase my frequency from a variable frequency drive to approximately 400 hertz, 8 times increase, which means my NS will actually become from 3, it was supposedly a 2-pole machine, my machine speed of NS will become from 3,000 to 24,000, 8 times increase. This is a huge speed. And these type of speeds are required, for your information, these types of speed are required in your centrifuge. जो आपकी uranium की enrichment है, the uranium enrichment by a gas, the gaseous centrifuge, it requires a high speed turbine, a high speed motor, and that is requiring 24,000. You can't do it by a gearbox. You can only do it by frequency over there. Now problem over here, अगर आपने frequency को 400 hertz कर दिया है, इसका मतलब यह है कि आपको voltage को भी 8 times multiply करना पड़ेगा. Now if you give a machine 8 times the more voltage, वो डैमेज हो जाएगी. Its insulation is not made for that purpose. So unless and until your machine is designed for that voltage, then you are going to do this one. Otherwise, you are not allowed to do this one in your machine. So when you are going to have an increase in frequency, this is a very important point. When you are going to have an increase in frequency, आप voltage को increase नहीं करेंगे. Why? Because your machine is only designed for 230 volt. It cannot take that voltage. Unless and until your machine is designed for higher voltage, it has that insulation strength, then you can do it. But yes, when you are talking about something, a frequency decrease, then yes, you will do a voltage decrease. Because that is possible. आप एक 230 volt की machine को 110 पे चला सकते हैं if you are halving the frequency. So this is very possible that your frequency, when it is decreasing, your voltage will be decreased. But when your voltage or frequency is being increased, you are not going to have a voltage increase because of the insulation strength of your winding. Now the question over here, very important one. Let me take this off. How will the torque slip curve change? This is your torque slip curve. Here I have this torque slip curve as the main basic torque slip curve over here. Now based on this data, can you tell me what is NS for this curve? 1800. It is being touching at 1800. So this means NS is 1800 RPM, and since this book is having a frequency nominal of 60 hertz because this is written in US, so you are having a frequency of 60 hertz. So from here you can easily tell the number of poles are 4. Now when you are going to have a frequency change, अब मैं यहाँ पे क्या किया है, the frequency is closer to, no, we don't have the exact value, it is something 1350 or 1375. Now what you can see over there, when you are changing the frequency, the curve changes to this shape over there, and this shape has a smaller pull-out torque. And why this has happened? Because you have reduced down the frequency of your stator. So your pull-out point has also, because this T pull-out is proportional to V Thevenin, and V Thevenin is proportional to your V phase. So when your frequency was decreased, you also decreased your phase voltage applied, or actually line to line voltage applied to your machine. So, and if you continue to decrease this one, you see all the curves, they are going down. So you can see when you are designing a machine, you have to tell the user of that machine that when you will decrease the frequency, what will be the torque maximum that you can take out. Now, when you go in the industry, many of you will be in the motor industry somewhere. Now, motors are used not just in maybe few industries, they are everywhere. They are in the steel industry, sugarcane industry, the cotton industry, the textile industry, or the glass industry, you name it, everywhere. So now, whenever a machine is, supposedly you are procuring a machine, आप एक machine design कर रहे हो, you are procuring a whole plant. So आपके पास as a designer, you will be asked, okay, how much machine torque you require. Supposedly, आपसे mechanical engineer ने आपने क्या दिया कि he has told you, you require a torque of approximately 10 Newton meter. Now 10 Newton meter, he must have to tell you that the speed at which that torque is required. This is very important. Because maybe if you are in the cotton industry, yes, you require a constant speed. There is no issue on that one. But when you are in the glass industry, or maybe you are in the steel industry, your speed changes. And when that speed changes, your torque has to be equal to that, even that speed. So what I mean by, if you are supposedly designing a plant over there and you are required for supposedly this much torque. So you are going to select a machine so that it can even run at approximately 180 RPM and it can still give you that required torque over there. So आप एक ऐसी machine नहीं पकड़ेंगे which is going to have something like this, और उसका torque आप कहते हो हाँ जी मैंने यहाँ तक पकड़ लिया, or maybe your requirement was something here, so you got something, a machine according to this point. But the same torque will not be possible in lower frequency range. So you have to first of all talk or design on the paper that at which speeds you require that much torque. So these curves are required. These type of curves are required from the manufacturer of any machines, so that you know that how this torque changes when the frequency. Now this is the curve where you are doing frequency change, but also doing the voltage reduction. The second type of curve which you are getting over here is when you are increasing the frequency. But here again, the voltage is reducing. The voltage is again over here reducing. So the V Thevenin is again reducing over there, because what you are doing over here, your V is constant. Your V is constant. Why? Because V by F ratio, I told this has to remain constant. आप F बढ़ा रहे हो यहाँ पे, लेकिन आप voltage बढ़ा नहीं सकते, because the insulation factor is there. So V by F ratio is reducing. Remember, in any electromechanical device, if V by F ratio reduces, you are actually having a output decrease from your torque. And that is the same thing happening over here. You are having this torque reduction over here. So if you combine these two curves over there, you can easily have the form of these two curves over here. This one, and in this one you can easily see that this one is the main curve at which the machine is designed. But if you change the frequency, you are actually going to have a reduction here. But you can see the difference. अगर आप frequency कम कर रहे थे, आप voltage को भी कम कर रहे थे. So the reduction is very small because the flux remains constant. But when you are having a frequency increase, आप voltage को constant रखा हुआ है. So the decrease is large for obvious reason. So this method of speed control is the best, in which you are using a variable frequency drive, or this is also called in some electrical terms as a cyclo converter over here. Because cyclo converter means the device which can actually change the frequency. So you take 50 hertz in and you can have something from 0 to 400 hertz as an output. This type of device is called as a variable frequency drive, or ASDs also. These are technical terms over there. We will understand them when you go in your final year, which are called as adjustable speed drives or variable frequency drives. But the more technical term on the electronics point of view is a cycloconverter. So if I go back to your lecture, when we are talking about the speed control method, if I name them, one is the frequency, very, very important. Your frequency is the most important factor for which you can actually change your speed. But remember, a variable frequency drive, which has the option of changing the frequency also and the voltage also, that is better suited for your device. There are something in the market, maybe Chinese or something local production also, which only change the frequency, they don't change the voltage. So that's a little problematic for the machine can burn out. So one is the frequency. The second one is the applied voltage, which means the phase voltage. I have told you that this is not linear. This is not linear control for obvious reasons, because you are doing this for your dimmers in your homes also, and that dimmer is not giving you linear control because torque is proportional to V Thevenin of square over there. So you are having a not linear control. So sometimes when you decrease down your dimmer, it's a single phase, 3 phase पे भी apply कर सकते हैं. You can do the very same thing. किसी को idea है what is that dimmer में हो क्या रहा है? For example, any idea? आप dimmer से जब change कर रहे हो, पंखे की तरफ क्या हो रहा है? What is happening electrically? Again, anyone? Current change होता है. Current किसकी वजह से? Voltage वजह से change हो रहा है. नहीं, resistance नहीं change हो रही. You are actually having, let me just give you an idea. You are having a sine wave applied to your fan. ठीक है? There is a device, I'm not going to go in very much detail. There is a device called as a Thyristor. Thyristor actually controls कि waveform को ये पूरा का पूरा this yellow part is going to go towards the fan, or it is going to turn on at an angle part, which means supposingly I on my circuit at 30 degrees, for example, and in the negative part, I also turn it on at something 180 plus 30, this is 210 degrees. So now the applied voltage which I am applying to my machine or that fan, let me make it again. So your machine is having something like this. So it's not a pure sine wave. It is a discontinuous sine wave where what you have done, you have taken this portion out of your circuit and now it's a discontinuous. और यही वो reason है why, because when you reduce your dimmer, what happens, a point comes, supposingly, let me mark that over here, supposingly आपने यहाँ तक angle कर दिया उसका, this shaded portion, the pink color, आपने यहाँ angle कर दिया 150 degrees, so only this portion is going, which I am making is as shaded, and this portion of the voltage, the pink color one, is so discontinuous that the current which is going towards the fan is also discontinuous. So the machine is only rotating, and you can even count the blades of your fan lying underneath it. So the machine is so dimmer is actually changing this angle from 0 to 180 degrees over there. Now the practical control is this, that if you are having a sine wave, I want the magnitude to change. So I wanted that magnitude changes like this, then I want to reduce it, it changes like this. But for this type of a circuit where I want to actually change the magnitude, I actually have to install a variable resistor. And that variable resistor has to have a power rating of that value also. Because if a fan is rated 100 watt, this means that 0.5 or 0.6 ampere current has to flow through that resistor. And you have worked on those resistors in your lab, and I have told you already that they are very expensive. So practically, and I don't know, since you are not that much, you are just in 20s over here at present, but like 30 years back or 25 years back, there were some dimmers over there, and those dimmers, okay, my pen has gone. Okay, those dimmers were having a variable resistor over there, and that variable resistor was used to control the fan speed over there. Nowadays they have been just reduced to those small dimmers which have a power electronic circuitry inside it, and they are the Thyristor's control over there. You will understand, you will go through this circuitry when you go in your, I guess, the 6th semester or the 5th semester in your power electronics course over there. So this is the speed control. The first thing, frequency. The second thing is the voltage, and these two methods are the best methods for speed control. Pole changing is also one, but that is obsolete, as I told you. Please kindly go through this article number 365 on page number 365 and 366. Kindly just give a read. These methods are obsolete, but still under study sometimes, or in some machines if you are encountering an old machine over there. So this is all for today. We have done the speed control, the pole changing, article number 6.6 and article number 6.9 over here.